Hello everyone, welcome back to my channel Experience Physics. In the last lecture, we have seen about electric current, the definition of electric current and the various ways of calculating electric current, average value of electric current, instantaneous value of electric current, supported by few numericals we have done. So according to the definition of electric current, the electric charges have to flow through a cross section of the wire per unit time. Right? They have to move. They must be put into motion, some velocity. Right? If they are static, if they are stationary, no current is constituted. Right? So they have to flow with some velocity. What is that velocity? It is drift velocity. Right? So in this video lecture, we will see about drift velocity, their concept and the relevant equations, how they are derived from drift velocity. Right? First, let me take a piece of conductor. I will take a piece of conductor like copper or aluminum and I will put the two ends left free. Left free. I won't connect any wire or any battery to the conductor, piece of conductor, right? So this is one isolated conductor. This way. I have taken one conductor and I have left the two ends free. Isolated conductor. Let the length of the conductor is L and its area of cross section is A. Length of the conductor L and area of cross section A. No electric field is applied. No applied electric field. Externally, I have not applied any electric field. Just I have put the conductor in the vacant space or free space or in the air, right? No such electric field is available across it. Right? But around the conductor, temperature is available. Temperature is available because the room temperature, right? In the room temperature, the electrons will get kinetic energy from the thermal energy. We know the thermal energy is easily converted into kinetic energy, right? Thermal energy is easily converted into kinetic energy. Many examples we can quote, right? Take the case of, or if you are boiling water or some milk, you may notice that when the heat is increased to a level, all the water molecules or the milk particles will move here and there in random motion. The same thing will also happen here. The free electrons which are available in the conductor, after getting some kinetic energy from the thermal energy, because the room temperature is enough for them. The room temperature is enough for them to give the kinetic energy for the free electrons to move here and there. Inside the metal, they are moving here and there, right? Because you know the mass of electron is very, very low value. The mass of electron is only 9.1 into 10 to the power of minus 31 kg. Minus 31 kg. Such a low mass the electrons possess, right? So room temperature is quite enough for the electrons to move here and there. After the thermal energy, the temperature is converted into kinetic energy, right? So they are moving inside the metal, right? With some velocity, randomly, random motion, U1, U2, U3 up to Un. These are thermal velocities. If I take the average value of, put together all the free electrons, if I take the average value of all the electrons, I will get 0 as answer. U1 plus U2 plus U3 up to N divided by N. This will be a 0. Average velocity is 0. Because if one electron goes left hand side, another electron may go right hand side. One electron goes topwards, another electron goes bottomwards, right? Similarly, northeast direction, southwest direction, in all the electrons, in all the directions, there is an equivalent opposite direction is available. So some electrons may take the opposite direction. So if you put together to find the average value of this velocity becomes 0, right? This velocity is known as thermal velocity. So because of the room temperature only, they get this energy. The room temperature is converted into thermal energy. Thermal energy is in turn converted into kinetic energy. Because of the kinetic energy, they are moving, but they move in the random direction. They are moving in one electron goes this direction, another electron goes this direction. One electron goes this direction, another electron goes this direction, right? Randomly, all are moving in all directions, right? So the net velocity, average value will become 0. According to our definition, to constitute current, the charges have to move. The flow must be there. But net value is 0. So no current exists here. No current exists. No current exists in this case. It is isolated conductor. No electric field externally is applied. So the randomly motion cancels each and every motion. So the average thermal velocity becomes 0. No movement, no current. Right. So this is the concept of this is the conclusion of considering this case. Isolated conductor with no applied electric field, right? Then let me take the same isolated conductor. It is not yet been wired. Still it is not yet wired. Same isolated conductor, that means the two ends are left free. I am going to apply some electric field. Let us see what is going to happen if I apply some electric field across the conductor, right? Okay. This is my conductor. L is the length of the conductor. D. Cross-sectional area isolated. I am going to apply some electric field. External electric field. E field is applied externally. How it can be applied? It is not yet wired. But how we can get the electric field, right? Just I am putting one big positive charge here and another one negative charge here. We know from the positive charge electric field lines emanate and they end at negative charge, right? I have not shown in the first diagram, right? E field is just applied here. Let us see what is happening here, right? These are our electrons. 3 electrons. Now, in the previous case, no electric field was applied. Due to the room temperature, they were moving in random direction. Here, E field is applied, right? E field is applied. A force will be existed. A force will be available here. We have studied F is equal to QE. In our case, it is EE. Q is negative charge electrons. Please remember this formula. Whenever you see the E and E together, you must recall the force. Whenever you see these two E's together in the product, you must recall the force, Coulomb's force, right? So a force is now available here. This force will pull all the electrons to this side, E movement. Why it is moving this way? Opposite direction to the direction of E field. Always electrons move opposite direction to the direction of electric field. Why? So they are negative charge carriers. If E field comes in this direction, means there is a positive charge which is available here. There must be some positive charge in some area here. That is the source of this E field, right? So this positive charge is pulling the electrons, attractive force. This negative electrons will repel it. The positive charge will pull it. Or otherwise we can say the E field is pulling it, right? Anyway, electrons are moving opposite to the E field. In search of this positive charge, the electrons are moving inside the conductor. Well, what will happen? After reaching this place, the end, after reaching this end, they cannot jump out of the conductor. So all the electrons will be accumulated here. Negative charge. All the electrons will be accumulated. They will be staying here. Similarly, the positive charges will be accumulated in the far end, the right hand side, right? So the E field is pulling all the electrons towards it, against the direction of it. So the electrons cannot jump from this conductor. They will be stored here. They will be accumulated here. The equal amount of positive charges will be induced here. They are known as induced charges. Yes. Now there is no electron inside it. No free electron, in fact. There is no free electron. All the free electrons have moved to the left hand side, this end, right? So according to the definition of electric field lines, the electric field lines would emanate from the positive charge and insert the negative charge. So this is the theory, this is the fundamental thing only. So inside we have some positive charge, some negative charge. They are polarized. On one end positive charges are accumulated, another end negative charges are accumulated. So electric field lines now they are available inside the material also. This electric field I will write it as EI. This is externally applied E field. Let it be O, outside electric field. We have applied it externally. Inside it is induced electric field, right? So because of this E field, all the electrons have moved to the left hand side. Positive charges have moved to the right hand side. They are known as accumulated charges or induced charges. These charges are making some internal electric field, EI. It is opposite direction. It goes to left and right, left to right, it goes from right to left. So EI can be written as minus EO. So it is cancelling. Inside the material, the electric field is cancelled. The effect is cancelled. Cancelling effect. So inside the conductor, E is equal to 0. So that is the conclusion we are deriving in this case. In the previous case, isolated conductor, no electric field was there. So thermal velocity average value is 0. Here E inside it is 0, right? Next I am going to take the same conductor, but I am not going to put such positive charge and a negative charge externally. I am going to wire it and connect to a battery, right? Let us see it. What will happen? So this is the most important case of our discussion under this video lecture. Please listen to me very carefully. This case is very, very important. L, length of the conductor, and this is cross sectional area. Yes. This is a cross sectional area. Now I am going to connect a battery here. This is wired conductor, not an isolated conductor as we have discussed in the previous two cases. This is wired. Assume this is having some voltage V, right? This is positive polarity and this is negative polarity, these two terminals. The positive polarity will be available here, the negative polarity will be available here, right? Plus, minus, same plus and minus have been brought at the two ends of the conductor. Now some voltage is available. Now some voltage is available across the two ends, right? What we have seen in the topic potential, V is equal to E dot D. Scalar value only I have written. V is equal to ED. Instead of D, we are having L. So V is equal to EL, we can write. So E is equal to V by L. V is available, L is also available. So there must be E lines between the two ends. Between the two ends. Those lines, let me draw this way. E lines. E is equal to V by L, right? Now E is applied. The same Coulomb force will also come here. F is equal to E into E. The free electrons will move against the direction of electric field. So this is movement of free electrons. Only one electron I have considered. Let us discuss with only one electron. This electron is moving towards this end. Here it is wired. In the previous case, the two ends were left free. They are dead ends. So the electron cannot move out of the conductor. So no motion was obtained. No current was there. Right? Here, there is a circuit which is a closed one. The electrons will flow through the lines, the leads, connecting wires. It will come here, positive terminal of the battery, right? The positive terminal of the battery will attract all the electrons, but at the same time, the negative terminal of the battery won't retain the electrons. It will push away the electrons. So this will again reach the right hand side end, right? So this is how the movement is established and this is how the current is constituted. All the electrons will be moving towards the positive and the negative terminal will be pushing away all the electrons to the right hand side. All the electrons will be now come here. The electric field will pull all the electrons to the left hand side. So the movement of free electron, so because of the Coulomb force, it will move towards the left hand side. This is how electric current is constituted in this case. It is wired case, wired with a battery, right? In the previous case, we have kept two positive and negative charge, isolated charge. They were building the electric field. Now it is, again the electric field is established, but through a lead of wire, through a closed circuit. Through a closed circuit only we are doing this, right? Now, we are going to discuss about the velocity of these electrons. They are moving in this circuit through the battery. Let us find the expression for the velocity, that is drift velocity, right? So before talking about the expression for drift velocity, let us find the meaning of drift velocity. Why it is not simply velocity? Why it is called as drift velocity? Drift velocity. Why it is not simply velocity? So drift means to move slowly with the aid of external forces. To move slowly with the aid of external forces. It is according to the Cambridge Dictionary definition. So the electrons are also here moving very slowly. Let us find their speed. They are moving very slowly with the aid of external force. Yes, external force, Coulomb's force. Because of this electric field, Coulomb's force is developed. With that Coulomb force, the electrons are moving and they are circulating in the connecting leads. Fine, right. So before again finding the expression for the drift velocity, let us focus about their magnitude, its magnitude and direction. Its magnitude and direction. Drift velocity. Velocity is a vector unit, vector quantity. Yes. So it must have both magnitude and direction. Let us discuss the magnitude and direction before finding the expression for the drift velocity. Magnitude direction. Magnitude we will consider next. First we will see the direction, right? So this is our conductor. We were discussing about it. We know under the room temperature, all the free electrons would move in random direction, right? Now E field is available. Because of this wired battery, E field is available. E is equal to V by L. E field is available. So external field. This E field creates a force. Both E and E are available. It creates the Coulomb's force. It pulls all the electrons. Current is circulated, right? But in which direction it is moving? Don't expect all the free electrons will follow a straight path. From that end to this end, don't expect all the electrons would follow a straight line path, right? Assume one electron is available here. Initially, due to thermal velocity, it will try to move this way. Then the applied electric field will pull it to left hand side. Right. The green line is assumed if there is no E field, only thermal energy, the green line. If both temperature and E field is available, the yellow line. So this is the difference, right? Here only temperature is available. As we have discussed in the first case, due to thermal energy, it gets some kinetic energy. Because of this kinetic energy, it is moving. This is the green line. No E field. When I apply E field, now thermal energy is available and E field is also available. It is drifted to the left hand side or drifted towards the positive end. This is a positive end. This is called a drift. Drift. The next Now it is available here. The electron is now available here. Next it will assume it goes this direction. Let me draw a green line. But the E field will pull the electrons to this way. So application of E field is making the electrons to move in zigzag fashion and finally reach this end. All the electrons will come to this end, right? So this is the zigzag way of motion. This is how the electrons are moving one end to another end or against E field to constitute electric current, right? This zigzag motion. But if you take the average value of all the average value of velocities of all the electrons, you will get a unified direction. Unified direction. If you take the average value, that means only one direction. If you consider all the electrons independently, it will be a zigzag direction. If you consider the average velocity put together all the free electrons, it will be a single direction. Because when average value means you are considering with the directions, magnitude as well as direction, right? They are moving up, moving down, right? After the cancelling out, the right to left direction will be finally retained. Other direction will be cancelled out, right? So this is how we are getting the direction in only one direction against the direction of electric field. All the free electrons are moving. So this speed is, or this velocity is known as drift velocity. What is the magnitude? Right. If only room temperature is available in the case 1, the thermal velocity or thermal speed is in the order of 10 to the power 5 meter per second. This is if only room temperature is available. No E field. But here we have given the E field also. What is the magnitude? Here the magnitude will be very, very low. So that is why it is known as drift velocity. It is moving very, very slowly. It will be in the order of 10 to the power minus 3 meter per second. Such a low value. Look at this value. This is plus 5. 10 to the power plus 5. Only thermal velocities. But here it is 10 to the power of minus 3. So direction we have seen, it is only one direction, how it is obtained, right? So magnitude is very, 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 very low value, minus 3 meter per second, 0.001 meter per second, right? Look at how small value this is, right? Why its speed is getting reduced from this value to this value. If only thermal velocity is available, such a big number, but if both the values are available, thermal as well as electric field, it is coming down, 10 to the power of minus 3 meter per second. Let us see why it is happening. I am taking only one electron. Only one free electron I have taken, right? So thermal energy, it moves in random direction. E field, it pulls towards this end, positive end, V voltage, towards this end. Yes, it is moving zigzag fashion, right? Inside the material, after the free electrons left to their respective atoms, positive immovable ions are there. See, in the atoms, in the outermost orbit, valence electrons are available. Upon the application or availability of temperature, the electrons are liberated from their respective atoms. Not all the electrons are liberated. Only few electrons are liberated. They are known as free electrons. That concept you know, right? The remaining part of the atoms, they are known as positive ions. They are available inside the material, in the atomic lattice, everywhere, right? The electrons now on their journey to reach this end, they will collide. They will collide with the positive ions. On their journey to the left hand side, they are encountering the positive ions. They are immovable ions. The remaining part, they can't move. The positive, they can't move. It is moving, right? If it comes with high speed, it will move the positive ions and it will stop immediately. Again, it is bouncing back. Stop immediately, then it is bouncing back. Then E field is pulling the electron, right? It is moving, it is stopping, then stopped by positive ions, then it is bouncing back, rebound of electrons, bouncing back, then they are pulled by E field. Pulling means in this direction. Randomly they may go any direction due to the thermal energy. But electric field is pulling against its field, against its direction, right? So the electrons are moving, it is colliding with the positive ions, then it is slightly bouncing back, then it is pulling. So this phenomenon is happening all the times. All the time it is happening. That is why its speed is reduced. 10 to the power minus 3 in the order of 10 to the power minus 3 meter per second. If E field is not available, if E is not available, this is 10 to the power 5 meter per second. This is because it is moving, stopped by positive ions, bouncing back, pulled by E field. These list of things are happening for every electron frequently, successively, continuously. That is why its speed is reduced. This is drift velocity. That is why we are using the word drift, to move slowly, right? So people can ask one question. When the electrons are moving, free electrons, millions of free electrons are moving, will any collision between electron to electron occur? The collision occurs between an electron and a positive ion. Okay. There are millions of electrons are moving inside the material. Any collision occur? No. No collision occur in electron because they are negative charge carriers. They repel. The electrons would repel the neighboring electron, right? So collision between electrons won't happen, right? In the immovable positive ions only the collision happens. So this is the reason why such a low value of drift velocity, right? When velocity comes, the time factor is also coming. When velocity comes, the time factor. But here, the time, let me introduce a term. It is relaxation time. One term I am going to introduce, this is relaxation time, and it is denoted by the letter tau. Let us see. what is this relaxation time, right? One electron is there. It moves zigzag direction to reach the positive end of the conductor. This is on positive ion. Collision. Then from here it moves here. Yes. Another positive ion. This is another collision. This first collision and this is second collision. So relaxation time is nothing but the average value of time interval between two successive collisions. Average value of time interval between two successive this is the definition for the relaxation time. Why it is called with the word relaxation? Because when it collides with the positive ion, its speed is almost become zero. Relaxation. Its speed is almost become zero. Then it rebounces. How it is rebounding? Due to the thermal energy. Then it is pulled by the E field. Right? Then it is again moving. Right? So that is the meaning why it is called as relaxation time. Right? This is tau. Right? Then we will find the expression for drift velocity, right? Using this concept what we have seen here, let us find the expression for it, right? I will start from the fundamental kinematic equation. V is equal to U plus AT. The T we will use the letter tau. U plus AT, right? For each electron, I will write V1, U1 and tau 1. For the second electron, V2, U2, A into tau 2. So, don't write A1, A2. A is always constant. Why? A is equal to force by mass. Force is equal to E by M. Charge on electron constant, applied field constant, the battery value we have not changed. So M mass of electron constant, all are constant, so A must be constant, right? Don't write A1, A2, A3, right? So up to Vn, Un plus A into tau n. If we take the average value, V1 plus V1 plus V2 plus Vn upon n is equal to U1 plus U2 Un upon n plus A into tau 1 plus tau 2 tau n by n. So this average value, this is the velocity of electron, right? Drift velocity is the average value of all the electrons collectively. So this is Vd. u1 plus u2, this is initial velocity. This is due to the thermal velocity, right? In the first case, we have derived that, or we have seen that the average value becomes 0 because all the electrons are moving in random direction. Easily we can put 0 plus A into, this is tau average or simply tau, right? We can write tau. So Vd is equal to A tau. So velocity is equal to acceleration in a time, right? That format it must come. Drift velocity is equal to A into tau. Vd is equal to A into tau. A we can write force by mass, force Coulomb force, E and E into tau. This is the equation for drift velocity, simple. Force by mass into relaxation time. If you want to write it in vector format, Vd bar is equal to minus E upon m tau, scalar vector. So this is with minus sign, negative charge carriers, right? So the expression for drift velocity. This is the expression for drift velocity, right? Now electrons are put under some velocity, drift velocity. If they move, current is constituted. So let us find the equation for current, right? So before finding the equation for current, I am going to introduce one term, free electron density. Free electron density, right? How many electrons per meter cube? That's all. So this is denoted with the letter small n. So please remember, we have used for the total number of electrons the capital N. This is small n, right? N is equal to number of electrons per meter cube. So this is number of electrons per meter cube. Density, right? For a given material, copper or aluminum, for good conductor, how many electrons are available for 1 meter cube of volume only, not for the entire volume. This is N. So removing the dimension, the specific value is written as N. So N must be constant, the small n. Capital N may be variable. The length of, if the area of cross section and the length of the material is varying, the capital N will vary. The small n won't vary for the material. Material to material it may vary. For the same material it won't vary. So number of free electrons per meter cube. This is free electron density, right? So let us find the equation for current. I is equal to Q by T. Rate of flow of charge. Q is equal to N into E. Yes, here I am using capital letter N. So total number of electrons available within the entire material, capital N, right? N into E. So I am rewriting this with small n. Then small n must be per meter cube. This is per meter cube. It must, so this is nothing but n by volume. Number of electrons, total number of electrons per volume. So n is equal to n per volume. To find n, you have to multiply these two terms. This is what I am doing here. N into volume multiplied by the charge of the electron divided by T is equal to N into volume. So it's a cross-sectional area, length, volume. NaL into E by T. This L by T, it has a unit meter per second, right? L by T, velocity. Meter by second is velocity. So what velocity? Drift velocity. EAN VD. VAN L by T is written as VD. So this is I. So I is equal to E, or let me write N A VD. Expression for the current. Q by T, NE by T, then using the volume I am converting it. So this is a expression, most important expression in this chapter. I is equal to ENA VD, right? Let me bring the A to the left hand side. I by A. I by A is equal to EN VD. This is known as, this left hand side term is known as current density. Ampere per meter square. The unit is ampere per meter square. Current density, which is equal to En multiplied by Vd. What is the use of it? This is written with the letter J. I by A is equal to En Vd. This is current density. This is written with the letter A. J is equal to En Vd, current density. We know area is a vector, right? So this is also a vector. J is equal to En Vd. That means in a conductor, all the electrons are expected to flow through the normal direction of its cross section. If they are flowing normally to the area vector, the current density, this is defined, right? All are expected to flow normally. If it changes, its value is also changed, right? So usually all the electrons, average value of electrons only we are calculating, average value of velocity only we are calculating. So all the electrons are expected to flow normally, right? If any change mathematically given, we can adjust using the formula, right? J bar is equal to E and Vd, right? If you write J bar here, then you must also write Vd. So this is current density. What is the use of studying this quantity? The current, okay. Current density, what is the use of it, right? Let me take a two conductors. Same amperes, but the current value is same, I is same, right? So all the free electrons, so if I is same, the number of free electrons are also same, right? All the free electrons have to pass through this cross-sectional area only. Here all the free electrons have to be passed through this area. So here more dense, here it is less dense. The flow is more dense. Within the given area only, all the electrons have to pass between the end to end. But here, they can move very relaxedly. In a relaxed manner, they can move. Less density, right? So, then what? Then what? Vd is, drift velocity is more, drift velocity is less. So, this is only changing. So, if area of cross section changes, Vd is, if cross sectional area is less, Vd is increasing. If cross sectional area is more, Vd is decreasing, right? It is like opening the door. So all the students have to exit from the narrow door only. If the door is wide open, they can move without pushing one another. They can, it's the same concept, nature law, same concept only the electrons are following. Right? So current density, it is how dense the flow of electrons is making. Right? This is more dense, small cross-sectional area. This is less dense, big cross-sectional area. Right? Next, mobility of electrons. Mobility of electrons. The meaning is how quickly the electrons move through a conductor under the influence of E. How quickly they move, right? We have seen if we apply external electric field, the electrons would move. How quickly they move? Mobility, mobile, right? How quickly they are moving, right? So this formula, let me write it again. Drift velocity is equal to force by mass, Coulomb's force, E into E by mass into relaxation time. This term is important here, this relaxation time, right? What are the factors which are affecting relaxation time? Before going to see the mobility, let us see the factors affecting relaxation time. Number one, temperature. This is the most important one. This is the most important one, right? If temperature increases, room temperature, if temperature increases, thermal energy would increase, in turn kinetic energy would increase. If kinetic energy increase, the speed of electrons would increase. If speed of electrons increases, they quickly collide with the positive ions. Collision increases. Collision increases means frequent collision, which is equivalent to frequent collision. Frequent collision means relaxation time decreases. It happens very quickly, so the time becomes small. So T increases, tau decreases. Inversely proportional. Tau is inversely proportional with temperature, number one. Number two, the material. Material, copper or aluminum material, because copper has more free electron density than aluminum. We know N value for copper is 8.5 into 10 to the power of 28. This per meter cube, per volume, per 1 meter cube. N value for aluminum is 6. So this value is varying, N value is varying. So more electrons, if I choose copper conductor, I will get more electrons. More free electrons means more collision, frequent collision, right? The time will be reduced. So number 1, temperature, number 2, material. But material, when we do the experiment, we won't change the material again and again, right? We will keep the experiment using only one conductor only. So the material, even though N depends on, tau depends on the material, this can be brought constant, right? If we choose for our entire experiment using the only one conductor, right, this will not be a big problem, right? Temperature, right? So tau is inversely proportional to the temperature, right? In this equation, if I or you or we keep the temperature it may confuse with current. If we keep the temperature constant, tau can be made as constant. If we keep the temperature constant, if we keep the room temperature constant, we can make the tau is also constant, right? Right. Come to this equation. Vd is equal to EE by m into tau, right? Vd is equal to EE by m into tau. Let me write E by m, tau and E. Just I am making or bringing tau inside. E constant, m constant. Now after keeping the temperature constant, tau is also constant, right? Only E is variable, electric field. If we change the voltage, E can be varied, right? So Vd is equal to, now some constants, all these constants are made as another constant. This is mu. Let us say this is mu. Mu is the mobility of electrons. Vd is equal to mu E. Vd is equal to E by m. E I am writing here, tau. These three can be, E and m are always constant. Tau, after keeping the temperature constant, tau is made as constant. Only thing is E, Vd is proportional to E. This Vd is equal to mu into E. Mu is known as mobility of free electrons. Yes. So this is also one important formula. From here we can write what is mu. Mu is equal to Vd by E. Its unit is Vd, meter per second, and this is E is equal to V by L, voltage per meter. Meter square, this meter will go up, voltage second, unit of mu. Meter will go up, meter square, this is second, voltage second, unit of mu. Meter square upon V dot S, Vs, right? So mu is nothing but the mobility of electrons, how quickly the electrons are moving inside the material upon the influence of electric field, right? Now E is the only variable. How E is varied? By varying the battery value, right? So this is L, V by L is giving me the electric field E value. So Vd is equal to mu into E only. If temperature is constant, mu is constant. Only thing is E is making the drift velocity variable, right? If V is kept constant, everything is constant, right? So let us find the equation between V and I now. Relationship between Vd is established, current is constituted, right? So let us find how the current is constituted by the application of electric field. How electric field was obtained? By connecting the battery. That is why I am interested in finding the relationship between V and E. I is equal to E N A by Vd. So E I cannot change, N I cannot change, constant, area of cross section, no connection with the V, only thing is Vd. E N A Vd I can write E by M, force by mass, tau, right? This can be rewritten as N, then E square, then tau upon M, then A into E. This is I. Here A I cannot do anything. E I can rewrite N E square tau by M A. This is V by N. This is I. So let me write V by I. V by I, cross multiplication. M will come here. Then this part will go down. Then L will go up, A will come down. Yes. V by I is equal to M over N E square tau L by A. This is a constant. Yes or no? Mass of electron, material, same material, N, electron density constant, charge constant, tau. We have assumed the temperature is constant, so this is also constant. Only the dimensions are available, length of the conductor and cross-sectional area. So this constant can be put into some other value as rho. Then this V by I, it is popularly called as the ratio resistance. We will come back to the topic resistance in detail in another video. Resistance is equal to rho L by A. So this is known as rho, known as specific resistance. Or resistivity. Or rho is equal to specific resistance or resistance. This resistance is the full resistance, the resistance of the material, right? If I keep L is equal to 1 meter and A is equal to 1 meter square, let us see what is happening. R is equal to rho. L is equal to 1 meter, A is also 1 meter. So this is R is equal to rho. So specific resistance, it is this way defined. Specific resistance is nothing but the resistance of the material having 1 meter length and 1 meter square cross-sectional area. Resistance of the material having 1 meter length and 1 meter square cross-sectional area. That is specific resistance or resistivity, right? Okay. I by A current density, I am writing again. I by A is equal to En Vd. So this is current density En. Vd also I want to expand E by M tau. En, Vd is EE by M tau. So this is N E square tau by M E. So actually J is a vector quantity, but I am writing the scalar values only. If you want to write it as a vector, you must write E bar, electric field vector, right? So here specific resistance or resistance, we have seen it as rho L by A. The rho is M upon Ne square tau into L by A. Here Ne square tau by M, it's coming along with E to define current. This is M over Ne square tau. This is Ne square tau by M, right? This term is written as sigma. This is rho. Rho is equal to M over Ne square tau. Sigma is equal to Ne square tau by M, right? So I will write sigma is equal to 1 by rho. So this relationship I am establishing. That is why I am rewriting this equation and I have come back to write it. I by A current density, right? Vd, if you expand Ed, you are getting this. This is nothing but the reciprocal of specific resistance. Specific resistance is, the reciprocal of specific resistance is called as conductivity, sigma. So this is conductivity. Conductivity of the material. Resistivity, it opposes the current. Conductivity, it helps the current to flow. Reciprocal, right? Then last topic, microscopic form of Ohm's law. As I told, I will come back to the topic Ohm's law in a different video, but let us keep in mind the V by I is equal to R. This Ohm's law, we will discuss it elaborately in another video, right? V by I is equal to R. So this is microscopic form of Ohm's law, right? J is equal to sigma E. J is equal to sigma E. Just now we have developed. J is equal to I by A. Current density, I per unit area. Sigma is equal to 1 by rho. E is equal to V by L, voltage per meter. Then if I take this ratio, V by I will get rho L by A. Rho L by A, cross multiplication. V by I is equal to rho L by A. So this is V by I is equal to R. Already we have defined rho L by A is R. So from here, I have derived this equation, Ohm's law. This is macroscopic form. This is macroscopic form. And this is microscopic form. Ohm's law we can write in two ways. V by I is equal to R, macroscopic form. Both are equivalent. This is microscopic form, right? Why it is called as microscopic form? It includes the dimensions. Look at it, area, L, but here dimensions are not here. voltage, current, resistance. But it includes the current with the cross-sectional area, E voltage with the length of the conductor, right? That is a microscopic form of Ohm's law, right? So this is the end of our discussion in this video lecture, right? Hope you have understood all the concept what I have discussed with you in this video lecture, right? Thank you for watching. Good luck to you all.